Welcome everybody. We're going to do a run through of all of the AP Physics C equations, and so we'll kind of go chronological, so that way if you want to skip ahead to something you need, you can move ahead. So let's just start with the basics. On your front page, remember some things you got. You have masses on the front. You have electric charge, easy one to forget. And then what's the other one? Gravity. We're going to be using 9.8 on this AP exam. Multiple choice, you can just use 10, and they're going to have the answers different enough that you'll notice the difference. The other one we're going to use is vacuum permittivity, and we're going to use that a lot. Permittivity, I got to say it right. And then we also use vacuum permeability in Coulomb's constant. So those ones we are going to be using. And as we do Gauss's law, you'll see where this turns into K a lot. Those are the big ones you're going to see. Here's just a reminder of all your different units. Here's your prefixes. And then it's always good to remember, make sure you're in degree mode, except when you're doing rotations. When you're doing rotations or simple harmonic motion, then you want to get back into radian mode. Okay, so just a quick reminder on that. All right, we're going to start this thing off on the very last page, looking at calculus. I know we said we're going to go in order, but quick reminder that your derivatives of natural log is 1 over x. Derivative of sine is cosine. Derivative of cosine is negative sine. And this is just a reminder that if I have a coefficient in front of my term in here, that gets pushed out to the front. This is the power rule. So this is like what is the integral of x squared? Dx will be x cubed over 3. And so they write it weird, right? So you add a power, n plus 1, and divide by that power, n plus 1. This is the one that comes up every now and then. So the integral of, this is really 1 over x is just natural log of x, okay? And then here, anytime you see a x here, it does not mean multiplication. It means cross product. And so when you do a cross product, what you'll have is signs involved. And so that's going to be my torque equation, force times distance times sine. But then it'll also be, what's the other one? Force equals Bill. So it doesn't say it, but you'll see that the cross product is going to be involved. So anytime you see this x, it doesn't mean multiply, it means cross products. So keep that in mind as we start to go through this. So let's see, here we go. Mechanics, let's start mechanics. A little blurry up there, here we go. One of the equations that's missing up here is delta x equals 1/2 v plus vt, and that's v initial and v final. And so these equations will all work when I have constant acceleration. So whenever I have constant acceleration, I can use these 4 up here. But when I have constant speed, I can be using displacement over time for velocity. So there's your tools. Next up, you got F net equals ma. All right, so they don't write it that way, of course. The next one's a weird one. It's force is dp dt. So that is the derivative of momentum. So if they give you a momentum equation in terms of time, what you can do is if you take the derivative of that, dp dt, you'll end up with the equation for the force. Okay, so that's kind of that relationship. This is one we've been doing AP Physics 1 and with C is that if you take the integral of the force in terms of time. So in other words, when you have a graph and you go to find the area, well, integral is area. And so that area of force and time is going to be your J. And J, if you look on here, stands for impulse. So really, this is just impulse. Okay? And impulse equals change in momentum. So change in momentum equals impulse. Change in momentum equals impulse. So this one here is P equals mv. So right here, we're kind of living in a momentum world. So this is really mv plus mv equals mv plus mv. Now, the one time we got to expand a little bit on that is what happens if I have like a weird, really weird game of pool where 2 balls then hit each other and then go off at a direction. So when these, like, let's say these are clay, right? And then they get together and then they end up being one big hunk of clay later. Well, what I would do is I would take my X direction momentums and my Y direction momentums. And thank you. Oh my gosh. I take my X direction momentums and my Y direction momentums, and those will be conserved because I have no outside forces. So I could take my X directions and I take my Y directions off screen, and those will be conserved, okay? And so that's all you got to do these. So this guy is in my X direction, so that ends up being here. This guy is in the Y direction, so that guy is in here. That's 0, and that's 0. But afterwards, both the masses are stuck together. So now you know how fast it's going in the X direction, and now you know how fast it's going in the Y direction. And so now you know these two components, okay? And that's a theme you're going to keep seeing, is that if I ever have a vector, I can break it up into its components, v cosine and v sine. But here's the thing, this works for velocity, it works for momentum, it works for forces, and so we'll keep coming back to that, okay? All right. Hopefully this is helping. We'll keep going. All right, next up, we've got ourselves. Our next one on here is friction. So, I don't know why it's so blurry all of a sudden. So usually we write this as force of friction is mu times normal, okay? So this is saying less than or equal, because remember when we talked about when we have static friction, it builds up to a limit, and that's why it's saying it's less than or equal, okay? So that's what that one's there for, okay? Next one, we're looking at energy. So let's just highlight all the energy ones here. So the energy ones are going to be our next 5 down here. There's a whole bunch more, but that's kind of our basics. So let's see. There we go. A little blurry, but we'll make it happen. So the first one is work equals the integral of force through a distance. So normally we'll just say, hey, force times distance, right? But the one time that we got to be careful is when I apply a force in an angle. Well, if I apply a force in an angle, it's actually work is force times distance times cosine. If you look here, see that dot? If I go back here to my last page, you'll see that whenever I have a dot product, it's at the cosine value. So what it's doing really is it's, by doing the cosine, it's finding how much is in the x direction, how much is in the direction of motion. And so that's what your dot product does. Okay. All right, so let's see, work. So sometimes you will see this as with an equation, but a lot of times we'll see it with a graph. The area, because remember integral is area, equals the work. And work also equals change in kinetic energy. Okay, so as I transfer energy, I'm doing work. Okay. Let's see, next one's kinetic energy. You guys got that one down. Next one, power. P equals power. That is the derivative of energy. In other words, it's how quickly you do energy. So last year we said change in energy over change in time. But remember, we're dealing with calculus world, and so we say dE. So in other words, a change in energy, change in time. So if I had an equation for power in terms of time, so let's say I had a kinetic energy equation that was like, well, the kinetic energy is changing like that, okay? Not a horrible example, but gets the point across. Well, I could say, well, the power is the derivative of energy. And so I could just say, oh, it's derivative of that, which is 8t minus 0. And so that is my equation for power. Okay. Other way you'd see this is on a graph. Well, derivatives are slopes. So it'd be the slope of the energy graph. Okay. The next equation for power is force times velocity. And so it is so remember, it's the dot products, so they have to be in the same direction. So if I have an object and I push it and it's moving this way, I push it that way and it's moving that way, the dot product would give me the power that I'm putting into it. So picture like a football player pushing one of those like sleds out there. When they push in the same direction, it increases the kinetic energy, and depending on what that force is, depends on how quickly they transfer it. Okay, that's power. Next one is MGH, but if you look down further, down here you'll see the other one for energy. Okay, so energy is negative GMM over R, and this one here at the very bottom, That one's if I have a planet and another planet, or I have like 3 planets spaced out. I would use this equation here. And notice it's a negative energy, so that means it builds up towards 0 as you go further away. So the energy is negative. MGH still works, but whenever my G is changing, whenever my gravitational field is changing, I want to use this last one. All right, let's see. Those are kind of some biggies up on energy. All right, energy. Okay, we're going to keep going. Here we go. Let's see, we got our next one is acceleration with a little c. What that stands for is centripetal acceleration. So whenever I go in a circle, I have an acceleration towards the middle. Well, if I have an acceleration towards the middle, that means I have an F net towards the middle because F net equals ma. And the acceleration and the F net are in the same direction. So usually you're going to be using mv squared over r. This will be the net force perpendicular to motion, okay? Because notice, centripetal acceleration is all about that inwards piece, okay? So a couple quick ones to go over on this is what if I'm driving through a dip? What if I'm driving through the inside of a roller coaster? And what if I'm driving over a hill? These are my 3. Well, let's do the last one. And then my last one is what if I'm doing something crazy? Okay, so first thing you want to do is you want to go, okay, which way is my weight force? Just start with that. My mg's are all down on all of these, okay? Okay, start with that. The next thing is on this first, let's do this top one here. That my normal force would also be down. And so if I wrote an F net statement, I would say normal plus mg, that's my F net, equals ma, mv squared over r. Because this is F net equals ma. Okay, so this is my F net statement. Now watch, if I go slower, my normal force gets smaller and smaller and smaller. So I have a critical speed. And that critical speed is when mg equals mv squared over r. Okay. Now, this bottom one though, my normal force is going to be bigger than this guy. And so my F net statement is normal minus mg equals mv squared over r. This guy up here, I have to have an F net towards the center of the circle. Remember how we talked about that idea? It's got to be towards the center of the circle. Well, that means I have to have more force towards the middle, so my normal force gets smaller. So my F net statement is going to be mg minus n equals mv squared over r. Now lastly is, and lastly is this guy, is I have to have an F net towards the middle. So ready? So F net statements in the x direction equals ma. So the F net statement is normal force equals mv squared over r. But I also have to have an F net in the y direction. That equals ma. What's my F net in the y direction? Mg, but that is not a centripetal. So we just leave it as ma. Okay, so this will be your acceleration, which will be changing your speed. Okay, but this acceleration right here is going to be changing your direction. This one's all about direction right here. Okay. All right, centripetal, centripetal, centripetal. I think that's it. Before we leave forces though, what we've got is if you have something at an angle, okay, you could break it up into its components, okay? And then I could say this mg is canceled up with this vertical guy, and these two tensions horizontally cancel each other. So if I know, a lot of times you'll know like this angle, and you're going to have to do sine, cosine, and tangent to find the other sides. So that's if it's a simple case. Well, what would you do if it was both at angles, right? Well, here I would break this up into components. And the horizontals would be equal, okay? Because they're the only two horizontals, but this mg going down, I'm going to call this x, and I'm going to call this z. Ready? X plus z going up have to cancel out mg. That's different than this one because the one before, it was just this guy equals mg. Okay. The other tricky one that I've seen students not like is the lasso problem. If I had something, you got to imagine like the string and something going in a circle. Well, this is a circle, right? So when I'm here, I have a centripetal force in here. I have an F net towards the middle. But then I'll also have a tension along this string. And I'll also have a weight force down as mg. So on this triangle, I've got tension, I have mg. Well, if I break this tension up into two components, if I look, the verticals cancel each other out, but nothing cancels out the horizontal. That means my triangle looks like this. That's tension, this is mg, and then this guy is mv squared over r. Last one with forces is when I have an object on a ramp, okay? So I have a weight force straight down as mg, normal force is this way, and the force down the ramp will be mg sine of theta. The normal force will be equal to mg cosine of theta. And if it was at rest, I would have friction up here, and then that friction force would equal mg sine of theta, if it's at rest, okay? Last thing with forces is when I have systems, okay? So let's have this be a massless pulley. And so if I have these two things, I'm gonna call this M, I'm gonna call this little m. So this big M is driving it, so that's its F net, okay? Equals MA. Well, how much mass is accelerated? The little guy and the big guy both get accelerated, and so I could solve for the acceleration as mg over m plus m. And then you also have an Atwood's machine, right? So if this was little m and this is big M, well, now I would just say it's mg minus little mg, because now these guys are working against each other, equals m plus m a. Some kids some year will see this problem, and they'll be like, what the heck? Okay, cool, watch. M, big M. Ready? First thing you gotta do is kind of know which way it's going, okay? But if I just start with F net equals MA, again, these are all massless pulleys. F net equals MA, well, let's just say this guy wins, okay? So I would just say mg sine of theta minus little mg equals m plus m a. Now, what if this guy had a bigger force? Well, I would just switch these. That's it, okay? Forces, I feel like that's the biggie on forces. All right, we're gonna do a little bit of rotational world, do some simple harmonics, and then we'll call mechanics a wrap. So the first one is torque. Down here is R cross F. Again, cross means that it's gonna be sine. Remember how we've done right-hand rules? So R cross F, and so really all of our right-hand rules use cross products. So we didn't talk about the direction of torque, but it has a direction, okay? So torque equals R cross F. So R times F times sine of theta. So there's my torques. Okay, the next one down here is written weird. Torque net equals I alpha, okay? And what's important is, like, let's say I had a pulley with two things on it. What I would do is I'd find the torque from one, and I'd find the torque from the other one, and then I would subtract them if they're working against each other. If they're working together, I would add them up, but if they're working against each other, okay? This is where we start to see I right here. See moments of inertia, and so that's our next one down here, okay? And so I. So a couple different things. One is just I of a single object is just mr squared, okay? That's just of a single object a certain distance away around a pivot that's going in a circle. I would just say mr squared. Okay. The next one that's not on here is the parallel axis theorem. So the parallel axis theorem is I take the I of the center of mass plus md squared. Okay, parallel axis theorem. Lastly is make sure that you've gone through a few situations where you find the moments of inertia using calculus. So usually that's going to be a rod around a pivot. Okay, and so what you'll do here is notice how this is R and dm, but everything's going to be given about lengths. So one of the strategies is to do density. So density is mass over, we're going to do linear density on this one, is mass over length. But that's also true is dm over dl. So what dm over dl means is that little masses over little lengths will have the same density as the total mass over the total length. This is what we call uniform density, okay? dm over dl. So notice how this is a dm here. Well, one of the things you could do is you could substitute. So you could say, well, dm is lambda dl. Okay, so see, I have dm here. If I move the dl up, I'll get lambda dl. And then you're like, Shmir, that's useless because a lot of times these problems won't even give you lambda already. Watch this. R squared lambda dl. Well, what is lambda? Watch this. Lambda also equals mass over length. So a lot of times this is going to be our strategy is to say, hey, they gave me the mass, they gave me the length, that's my density, dl. Now notice, dl and r are both measurements. These guys are both measurements of distance. And so these guys can talk with each other. Whenever you're taking integrals, you can't do r and dm. They're not the same variable. You can't do that. What you can do is when you get r squared and dl, you're off to the races. All right. Next up, center of mass. It says the exposition of the center of mass. And what that's saying is that if I have an object, let's say I have multiple objects and they have centers of masses, I just pick a 0. I'm going to call this 0 and I'm going to call this 0 here. Okay, so this has a distance to this guy's center of mass. This has a distance to this guy's center of mass. And all I'm doing is I'm adding them up. So the x of the center of mass times the mass of the center of mass equals x1 m1 plus x2 m2. Okay, and so you'll see it, they just write it as summation here on the equation sheet. That's what that guy is right there. Okay, calculus. Could you also do calculus? Yes, you could totally do calculus. You could say the x of the center of mass, the mass of the center of mass equals, add up all of the little masses and their positions. Does this look like a lot like moment of inertia? Yes. Okay. All right. I think that's the biggies. Next up, so v equals r omega. Okay, so this is linear velocity and how it relates to angular velocity. Omega stands for angular velocity, which is change in angle over change in time. These need to be in radians. Okay, these cannot be in degrees. All right, which leads to the next setup is dealing with L. And if you look up here, L stands for angular momentum. So there's two equations for L. So you've got r cross p. We're going to talk about that one right now. And L also equals I omega. I think this one's going to make more sense because this is the figure skater, right? This is like saying the figure skater, when she brings her arms in, her I gets smaller, and so her omega gets bigger, okay? That's what I think we're used to, right? But this one here, you're like, what the heck is that? Watch this. What's P equal to? Momentum. So that is R cross MV. Well, that just means it's MVR. And as long as it's just perpendicular, so like let's say I had a pivot point and I had an object moving, I would just say it has pivot points and an object moving. I would say it has momentum. And if I multiply by the radius, I'll show how its effect is. Well, usually this is like I have myself a disc or something and I throw a piece of clay at it, right? When it hits, I would say MV times R, because if it hits out here, it has a bigger impact. If it hits in here, it has less of an impact. Okay. MVR. But notice it's a cross product, so it's actually sine. So you always want to look at the point in which it's perpendicular. When it's not perpendicular, that's like that multiple choice question we went over, you'll have to use the angle it's at. But you'll end up getting the same exact value for the point in which it's perpendicular. All right. Next one is looking at kinetic energy of rotations, which is 1/2 I omega squared. Okay. The next one is dealing with which this one really comes into This one really comes into play when I have an object rolling down a ramp without slipping. Okay. So there's two ways you could approach this. The easiest way is just to say, hey, I start with gravitational energy, and at the bottom I end with translational and rotational. That is the easiest way to do this. Let's just say this is a solid disk with an I of 1/2 mr squared. Okay? So I would just say mg, let's call this h, right? H equals 1/2 mv squared, which is translational, plus 1/2 I omega squared. Okay, so I get mgh equals 1/2 mv squared plus 1/2 I, 1/2 mr squared. Well, omega, what does omega equal to? Ready? Since v equals rw, r omega, that means omega is v over r. See how these m's are going to cancel? So I get gh equals 1/2 v squared plus 1/4 r squared's on top, r squared's on bottom, I'm left with v squared. So I get with gh equals 3/4 v squared. Okay? And so that's one way to do it with energy. Okay? So that's an energy way to do it. But the other option is I could also do this with torque world. Okay? Because when this guy's here, what is it that causes it to spin? It has a force of friction. Okay? And it has an mg also. So if I were to do force world, I get F net equals ma. So this is linear force world, and I could say mg sine of theta minus force of friction equals ma. Okay? Problem, you don't know how big the friction is. You're toast, right? Well, watch this. But if I go to torque world, torque is I alpha. Again, let's say this is a disk, right? Just so we have consistency. So we've got ourselves torque. Well, what causes the torque? Friction. Force of friction times radius, I'm going to say it has a radius to it, r, equals I, 1/2 mr squared times alpha. So I got force of friction is 1/2 mr alpha. I canceled one of those out. So now this is going to be the same. So now I can combine these two equations together because I know the force of friction equals that. I can substitute it in. Some of you are sitting there going, but what about the alpha? Well, already alpha is A over R. And that's not on your equation sheet, but it's a big idea. Okay, so I can substitute it. All right, last things on mechanics. So first one on the top is springs. So you'll notice these are all simple harmonic motion here. So whenever I have a spring, I could use Kx. Good morning. And then I could also use spring as 1/2 kx squared. And then, good morning, Mr. Lemberg.
Good morning.
Doing an equation run through video. Everybody's gone. Everybody's got AP tests, so we're taking a video, giving it to the class.
Oh, nice.
Yeah.
Just wanted to let you know I'm done with my test.
Oh, stop. He's just flexing because he's done. So the other one is period of spring is 2 pi square root of m over k. Okay, so what this means is that if I have a spring in a block and it oscillates, this magic spot in the middle is called equilibrium, okay, the equilibrium point, and then it goes x each way from equilibrium, okay? That x is going to define the forces and it's going to define the energy. So if they ask you how fast it's going, I want to do this one. If they want to ask you what the acceleration is, I want to do this one. If they ask anything about time, I want to do this one. Okay. Where does this come from? You ready? So in this situation here, the force of the spring equals kx, which is also equal to ma, which ends up being, if I isolate this, I get x over a equals m over k. So we're going to use that idea here. So if you look at my next equation here, you see x equals x max cosine omega t. Okay. Well, if I take the derivative, I have velocity. Well, the derivative of cosine is negative sine. But I have to take the derivative of the inside too, so I get an omega here, and I have my x max still. When I take the derivative again, I get acceleration. So derivative of sine is cosine. So I keep the negative x and end with cosine omega t. Oh, but I got to take the derivative of the inside too, so I end up with omega squared. Okay. So when I do x over a with this, x over a, I get x max cosine omega t over negative x max omega squared cosine omega t. If you notice, cosines go away, x max goes away, so the only thing that impacts x and a is omega squared. I always do this. I always forget the negative. Sorry. Okay? So if x over a is 1 over omega squared, well, watch this. If negative x over a equals 1 over omega squared, I got 1 over omega squared equals m over k. So omega squared equals k over m. That's big. We're going to use that because when I look at my next equation on here, I got period is 2 pi over omega. Well, what's omega? Omega is the square root of k over m. So that means period is 2 pi divided by square root of k over m. Well, what does that become? I get the period ends up being 2 pi times square root of m over k. But this is where it comes from. Okay, so that's where this comes from. That's where the equation comes from. Pendulum, similar process. You end up with L over G. Okay. Next up, we've got ourselves force due to gravity, which is good. Meaning I have two objects. They will have a gravitational pull on each other. Now, a lot of times we'll use this when we deal with orbits. So if this guy's orbiting, I could say that the centripetal force is caused by the gravitational force. So I could say mv squared over r equals gmm over r squared. Mass of the planet cancels, so I got velocity is the square root of gm over r. Okay, so that's one thing we can use. The other is this is going to be an elliptical orbit. If it's in an elliptical orbit, I say that IW equals IW, but since we're dealing with planets, I'd say MVR equals MVR. So as the planet goes from here to here it goes slow, here it goes fast, because as you change your R's, you have to change your velocities. This is momentum. This is one of Kepler's laws. Last Kepler's law is that the period squared is related to the radius cubed. Where that comes from is this equation. And what you do is you plug in 2 pi r over time. So if I plug that in, I got, ready, see I have v here? So I can just say 2 pi r over period equals the square root of gm over r. And all I got to do here is isolate it and end up with t squared and r cubed. Okay, that is a run through of everything in mechanics. The one thing that's missing is projectiles. Okay, that is not on here. And so projectiles, remember that whenever you have a projectile, anything launched in the air, look at horizontal and vertical. Horizontally goes constant speed, vertically does not. Okay, and so if it's just in free fall, your acceleration is gravity or negative g. And if I launch it horizontally off a table, this will be 0. But if I launch it at an angle, then this will be v cosine for the x and v sine for the y. Okay. I think that's going to call it good. Okay, I think that hits everything. Hits all your ideas. So there we go. We're going to make another one for E and M because that took a little bit longer than I thought. Go get them, guys.